Welcome to the lecture for Introduction to Mobile Robotics. We are now dealing with the module 2 of the course, and we've already seen uh, internal sensors that is being used for mobile robotics. Now we will see the external sensors that is being used for the various types of mobile robotics. External environment sensors enable a mobile robot to perceive and interact with its surroundings. Unlike internal sensors, which where we have seen encoders and IMUs that measure the robot's own motion, external sensors provide information about objects, obstacles, and movement in the environment. These sensors are essential for safe navigation, obstacle avoidance, mapping, and human-robot interaction. Among the external sensors, motion sensors detect movement of objects or people, while range sensors measure the distance between the robot and the surrounding objects. Together, they form the foundation of the robotic perception system used in autonomous navigation system. In this figure, you can see the basic arrangement where how the external sensors are being used for object detection or obstacles detection in a mobile in case of a mobile robotics. And here it's an application where it is being used where while it is moving it can find out the obstacle in its place and it can change its direction based on the position. Now we'll see the motion sensors in detail. We'll see the concept and working principle of motion sensors. Motion sensors are used to detect the presence or movement of objects within the robotics environment. They do not necessarily measure distance, but rather indicate whether something is moving and sometimes the direction or speed of motion. A common example is the passive infrared sensor, which detects the changes in infrared radiation emitted by warm objects such as humans. When a moving object enters a sensor's field of view, the detected IR pattern changes, triggering a motion event. Other motion sensors include Doppler radar sensors, which detect motion by measuring frequency shifts in reflected radio waves, and optical motion sensors, which analyze changes in visual patterns. Here we can see a PIR sensor, passive infrared sensor, which detects an object based on the radiation emitted by the warm objects. That is, each objects will have different kind of warmth will be generated from their body, and based on that measuring that we can detect whether an obstacle is there. This is one of the principles that is used by the motion sensors. We'll see what are the applications and limitations of motion sensor. In mobile robotics, motion sensors are widely used for human detection, intrusion, monitoring, collision, prevention, and interaction triggering. For example, service robots use motion sensors to detect human presence, while security robots rely on them for surveillance. Now we see the limitations. PR sensors cannot detect stationary objects and are sensitive to temperature variations. Radar-based sensors may detect unwanted motion such as moving machinery or vibrations. As a result, motion sensors are typically used in combination with range sensors or vision systems to improve reliability and accuracy. Range sensors concepts and type. Range sensors measure the distance between the robot and the surrounding objects, enabling obstacle detection and environment mapping. They operate by emitting a signal and measuring the time or intensity of the reflected signal. Common type of range sensors include ultrasonic sensors, which use sound waves, infrared sensors, which use reflected infrared light, and LIDAR sensors, which use laser beams for high precision distance measurement. Ultrasonic sensors are low cost and simple but have limited accuracy. LIDAR provides high resolution distance data and is widely used in autonomous robots, though it is more expensive. We'll see the role of motion and range sensors in robot navigation. Motion and rain sensors together enable robots to sense dynamic and static elements in their environment. Motion sensors alert the robot to moving objects, while rain sensors provide precise distance information for safe navigation and obstacle avoidance. In advanced mobile robots, data from these sensors is combined using sensor fusion techniques to create a reliable representation of the environment. This integration improves decision making, enhances safety, and allows robots to operate autonomously in complex and changing environments. Now we'll see the LiDAR. LiDAR is full form as light detection and ranging. It is an active range sensing technology used in mobile robots to measure distances to surrounding objects using laser light. It works by emitting short laser pulses and measuring the time taken for the reflected light to return after hitting an object. Since the speed of the light is known, the distance can be calculated accurately. In mobile robotics, LiDAR is widely used for obstacle detection, mapping, localization, and navigation. By continuously scanning the environment, LiDAR generates a detailed representation of nearby objects, enabling robots to perceive their surroundings with high precision. Now we will see the working principle of a LiDAR. A LiDAR operates on the time of flight principle. A laser pulse is transmitted toward an object and a photodetector measures the time delay between emission and reception of the reflected signal. The distance is calculated using the formula distance is equal to c into t by 2, where c is the speed of light and t is the round trip time. Rotating a solid-state LiDAR system scan across a wide angle, producing two-dimensional or three-dimensional point clouds of the environment. These point clouds are used by the robotic algorithms for SLAM, that is simultaneous localization and mapping and path planning. Here the figure shows the process of a LiDAR, where you can see there is an interaction between the radiation objects, and when the radiation, two signals are generated, either the radiation propagation through the medium and the signal propagation through the medium. Radiation propagation is received by the transmitter, and the signal propagation generated through the medium is sent to the receiver, that is a kind of detector, where it is sent to a system control and data acquisition module. This data will be sent to the transmitter and that to the main source where the object or the obstacles is generated. And also the data from the system controls will be fed to the data analysis and interpretation module also. Now we'll see the applications, advantages and limitations of LiDAR. LiDAR offers high accuracy, long range and fine spatial resolution, making it ideal for autonomous mobile robots and self-driving systems. It performs well in low light conditions since it is an active sensor. How LiDAR has limitations: it is expensive, consumes more power, and its performance may degrade in rain, fog, or dust. Reflective and transparent surfaces can also cause measurement errors. Despite these challenges, LiDAR remains one of the most reliable sensors for precise robotic perception. Sonar. Sonar is a sound navigation and ranging. It is a range sensing technique that uses ultrasonic sound waves to detect objects and measure distances. In mobile robotics, sonar sensors transmit ultrasonic pulses and listen for echoes reflected from nearby objects. The distance is calculated using the time of flight of sound waves, as we have done for the LiDAR, based on the known speed of sound in air. Sonar sensors are commonly used in low-cost robots for basic obstacle detection and proximity sensing. Now we will see the applications, advantages and limitations of sonar. Sonar sensors are inexpensive, simple and robust, making them suitable for indoor environments and educational robots. They can detect objects regardless of color or lighting conditions. However, sonar has limited angular resolution and accuracy. Soft surfaces may absorb sound waves while angled surfaces can deflect them away, leading to incorrect readings. Sonar is also affected by environmental factors such as temperature and air currents. As a result, sonar is often combined with LIDAR, IR sensors, or cameras for reliable navigation. Now we'll see the comparison of LIDAR and sonar. We are considering the different parameters. First is the working principle. In the case of LIDAR, we use laser light and time of flight of light pulses. For sonar, where we are using ultrasonic waves, we use ultrasonic sound waves and the echo time. Range. LIDAR has a long range, that is tens to hundreds of meters, while for sonar it is of short range. Accuracy. Accuracy is very high and resolution is also very high in the case of LIDAR, while sonar it is moderate. Environmental sensitivity. In the case of LIDAR, it is affected by fog, dust and reflective surfaces, and in the case of sonar, it is affected by temperature, air currents, and soft surfaces. Cost. LIDAR is expensive, while sonar is low cost. Typical use: mapping, SLAM, autonomous navigation, etc. For sonar, we use it for obstacle avoidance and proximity sensing.